Hello and welcome to Miss Ma's Grade 11 Functions class. This is a Chapter 1 review. So we're going to do some definitions first. A relation is a relationship between two variables, only two variables. So if it had three variables, it would not be a relation, or one variable. A function is a type of relation in which each independent variable, the x values, corresponds with only one dependent variable, y value. So every x has only one y. The domain is the set of all the x values, and the range is the set of all the y values. We're going to find the domain and range for each of these examples. So y equals x minus 5, this is a line. Most lines, almost every single line, has a domain of x in R with no limitation. So it could be anything in the reals. So we would pronounce this x in, or an element of, the real numbers. And to draw that reals, we just have to draw two bars and then an R. It's called the double bar R, and just differentiates it from, range or whatever else. And it means that it is continuous, so every single thing, every single number from negative infinity to infinity is included. And this also includes y in R, because every y value is included. Example B, x squared plus y squared equals 9. This is the circle. X squared plus y squared equals r squared. That's the typical equation of the circle. So we've got a radius of 3, because that's 3 squared is 9. So if you drew this out, you could see that we're centered at 0, 0, because we've got x squared plus y squared. And this is the circle. Let's just pretend that's a circle. And this goes from negative 3 to 3, because the radius is 3, and negative 3 to 3, and the y values as well. So as we go left to right, we can see that the lowest value we can get is negative 3, and the highest value is 3. So the domain is x in R, such that negative 3 is less than equal to x is less than equal to 3. Whoops, that's a really ugly 3. I'll redraw it. X is less than equal to 3, and the range is y in R, such that you can see the lowest we can get to is negative 3, and the highest bound is 3, so it's the same. Negative 3 less than equal to y is less than equal to 3. Example C, we've actually got this sideways parabola here, and it's not including the 3 because we've got an open dot here. If we had a filled-in dot, then we would know that we are including that value, but we're going up to but not including 3, as in 3.00001 would count, but not 3 itself. So you can see as we go from left to right, we don't have anything on this side, so the domain is x in R, and it is continuous because everything is touching. So x in R, such that x is greater than 3, but not including, so we don't have the little equals. And the range, well, it's everything up and down. There's no limitations that we can see, and if there was, then it would be indicated in the graph. So the range is y in R. No limitations. Okay, last one. So this is a parabola, if you recall. It's a parabola of the form, vertex form, ax minus h squared plus k. So we can find the vertex. It's 2, 4. And we also know that it's opening upwards because this is positive. There's no negative there. So this parabola is opening upwards. A parabola has the domain of x in R always, unless there's some limitation from a word problem or something like that. And then the range y in R, because it's a continuous function, such that, and we want to be greater than the minimum value, y greater than equal to 4. Of course, if this had been negative, then we would have put y less than equal to 4. Y less than equal to 4. But it's not. Okay, let's look at function notation. So function notation just uses f of x. So instead of writing y, we write f of x. Why do we do that? Well, we're just showing that x is the independent variable and f is the dependent variable. So f as a function of x, or in terms of x is what we would say. So this is not multiply, it just shows us that wherever we have x, we can replace it with whatever is here. So when I see x squared, I'm going to put instead 2 squared plus 3 times 2 minus 2. So I'm just copying wherever I have x, I'm putting the 2, and everything else is just staying the same. So squared, squared, this 3 and this 3, and this negative 2 and this negative 2, right? So once I found that, then I can evaluate this since I have only numbers. So 4 plus 6 is 10 minus 2, that's 8. It happens the same way with a negative number, but I'm going to put brackets in there because I don't want to do it incorrectly, so don't forget about order of operations. So negative 4 squared plus 3 times negative 4 minus 2, and I'm going to evaluate that, so 16, not negative 16, minus 12 is 4, minus 2, it's 2. And of course, inside of function notation, I can pretty much put anything that I want, any variables. I've got a little equation here, or sorry, expression here, and you can put that in as well. So instead of writing x, I'm going to write 2b plus 1, 2b plus 1 squared plus 3 times 2b plus 1 minus 2. And since this isn't all numbers, I'm not going to be able to evaluate it, but I can simplify it. So to simplify that, I'm going to just multiply 2b plus 1 times 2b plus 1, which gives us 4b squared plus 4b plus 1, plus 6b plus 3, because I'm just using the distributive property, minus 2. And then I'm just going to collect like terms, so I get 4b squared plus 10b plus 1 plus 3, 4, minus 2 is positive 2. And even though you could technically common factor this, you should not, because we are in the simplest form with no brackets, and you should leave it that way. The inverse, here's another definition for you. DFN just stands for definition. The inverse is the reverse of a function. In order to find it, you're just going to switch the x and the y, and then you are going to isolate y. That's all you have to do. So you'll notice that the inverse may or may not be a function. You could actually find the inverse also of relations. This is a relation. We're going to find the inverse of that. You can do it algebraically, and you can also do it graphically. So when we're doing it algebraically, we're just going to switch the x and the y and isolate y. Here you can see I actually don't have a y, but f of x is equal to y, as we just talked about. So we can write that as y. Y equals x minus 3 over 4. And then this isn't equal, so you should have a little separation and write, we're finding the inverse, you know. And we're going to reverse it. So instead of writing y, we're going to write x here, x equals, and then instead of an x, we're going to write y, so it's switched. So wherever you see x's, you're going to write y's, and wherever you see y's, you're going to write x's. And then going to isolate. So you just do your algebra properly in the correct order, and you get this, 4x plus 3 equals y. There we go. And I know that this is the inverse, so I'm going to write f inverse of x is equal to 4x plus 3. Remember that f inverse of x, this little negative 1, is not an exponent. If it was an exponent, then we would just put 1 over f of x. So if I have something like f of x in brackets and then to the negative 1, that's 1 over f of x. This is the reciprocal. It's not the same thing as the inverse. Okay, for example G, we're going to do exactly the same thing. So you take all of the points on the graph, so let's say this is something like 0, 1.8, and we're going to switch the x and the y. So the x here is 0 and the y here is 1.8, so we're going to draw in 1.80. And that's going to be on our inverse. And I'm going to I guess we could estimate some other ones, but I can also just kind of see from the shape what it looks like. I know it goes through 0, 0 as well. When you flip 0, 0, it's still 0, 0. And so I can just kind of draw it around the 2 points that I've got. You can see that our inverse really is not a function at all. Oops. Okay, you can pretend that it looks a little bit more like this. And that's our inverse. Another way, a third way that you could find it is just to actually draw a line, the line y equals x, and you can reflect over the y equals x axis. So I can see that I did this incorrectly, because I should be touching the inverse and the original function should be touching wherever we are at y equals x, because the inverse is a reflection over y equals x. That means that anywhere we're on y equals x, those are called fixed points, they stay the same, and anywhere else we're just flipping over. Now this is really hard to do if you don't have very good spatial reasoning like I do. I do not have good spatial reasoning, so that's why I like to just flip the coordinates. Okay, a parent function is the simplest function in a family of functions. So it's the very simplest whatever it is. Like if it's a line, it's the very simplest line that you can get. So you have to remember the line, the parent function is y equals x. It's the simplest because we have, you know, a slope of 1 and we have a y-intercept of 0. For the parabola, we get y equals x squared. For the square root function, y equals root x, and remember when you write root x, this is the positive version, it's not the negative version. If we wanted the negative, we would put plus minus root x, and it would look like a sideways parabola. So that's not the same thing. We don't want this one because it's actually not a function. If you remember, there's a vertical line test, and you just draw a vertical line down, and if it touches in more than one place, then we know it's not a function. So we wanted a function, a parent function, so we're just taking the positive version of the square root. I just want to point out some of the significant points of the square root function. We've got 0, 0, we've got 1, 1, and then we've got 4, 2, and if we were far enough, we'd also get 9, 3. So these are some of the significant points. You can see that they're reversed from the parabola, because in the parabola I've got 1, 1, 0, 0, those are the same, and then I got 2, 4. So it reverses to be 4, 2 in the square root. Alright, then we've got the reciprocal function, which is y equals 1 over x. We do have two significant points here. We should have 1, 1, and also negative 1, negative 1. And then we have two asymptotes. X equals 0 is right here, the vertical asymptote, and y equals 0. And lastly, we need to know the absolute value function, which is y equals absolute value x, and it looks like a v. And it just has a slope of negative 1 on this side and a slope of positive 1 on this side. So this side looks like y equals negative x, and this side looks like y equals positive x. The last thing we're going to talk about is transformations. The transformations of any function f of x will look like this: y equals a f of kx minus d plus c. You'll notice that this part is factored, and that's kind of important, but we'll talk about that in a second. Anything that's inside of these brackets is horizontal, and they work counterintuitively, and then outside of the brackets is vertical, because the inside is affecting the x is the horizontal coordinate, and you'd only have to worry about moving it sideways, and the outside is affecting the f, which, as we talked about, is the y part. So that's why these are the vertical parts. And please spell vertical properly, vertical, vertical. Okay, so the A is a vertical stretch or compression. It's called a dilation. And it could also be a flip, a vertical flip over the y-axis. It's a little bit counterintuitive there. The vertical, C is the vertical shift. And then I've got K, which is the horizontal stretch slash compression, and a horizontal flip over the x-axis. D, it's the horizontal shift. inside of the brackets, the horizontal is a little bit counterintuitive, what we call counterintuitive. It goes against your intuition, against what you think it should be. Counter meaning against, and intuitive meaning what is in by your intuition. And vertical, both the verticals are intuitive. So they do what you expect them to do. So for example, if I was thinking about something like y equals 2f of x. You can see this is outside the bracket. So it's a vertical, and then the 2, it's a stretch, because it's multiplied by 2, so it makes sense it's just stretched by 2. However, if I have the y equals f of 2x, now I'm on the inside of the bracket, so it's horizontal, and now it's counterintuitive, so it's actually against what you think. You think 2 times is stretch, but nope, that's wrong. It's actually a horizontal compression by 1/2. Okay? So we can transform parent functions to create child functions, to make the family of functions. That's where that comes from. And when you have this type of question, we're probably going to ask you to write the transformations in order and to graph it. When you graph it, I do expect you to show the parent function and some of the transformations as well in order to find the final product, the image function. So this has a parent function of y equals absolute value x, and it's got 3 different transformations going on. It's got the negative, so the vertical flip. We've got the +2, and it's on the inside, so you think +2 should be to the right, but it is to the left, too, because it's against your intuition. And then this +1, which is outside the brackets, intuitive, it does what you think it should, and it goes up 1. Okay, you're just going to have to memorize that order. So we're going to start with y equals absolute value x. I'm going to just draw that in there. That's totally wrong. Let's draw it again. Okay, there we go. And the other side of it. Okay, so that's y equals absolute value x. I think this is still wrong, isn't it? Sorry about that. Struggles. Okay, there you go. Just keep going until you get it right. That's okay. Okay, here we go. And we're going to label that, so you make sure you label your parent function, y equals absolute value x. And by the way, the more colors you have, the easier your life will be, because it'll be easy to tell them apart, and the easier you'll make my life, as I will be marking your stuff. Okay, so I'm going to do green, and I'm going to do the vertical flip in green, and then I'm going to do the left 2 up 1 together. So we're separating the dilations from the translations, from the shifts. So I'm going to do that green, a green vertical flip. So it's going to start on the same place because it's on the x-axis, and everything is going to get flipped over. So this was a positive one, it's going to get multiplied by -1 to be -1, +2 times -1 is -2, and so forth. You can see it's symmetrical, so it's going to be the same on the other side there. So this is y equals negative absolute value x. And then we're going to take, you always take the last graph that you did, and we're going to take that graph and flip it, or sorry, move it. We're going to move it left 2 and up 1. So you take all the points and we're going to move them left 2 and up 1. So take this point, move it left 2 and up 1. Take this point, left 2 and up 1. And once you have the shape, or the starting point, then you can follow the shape of the previous one. So I know this has a slope of 1, -1, 1, so I'm going to follow it. And everything else I'm going to just follow left 2 and up 1 using the last graph that you drew. And there you go. So I moved everything left 2 and up 1, and I'm going to label it. That's my last one. So y equals negative absolute value x plus 2 plus 1. One more example for you. we've got y equals negative 3 root 2x plus 8. Now this is a little problematic because actually we need to have brackets in there. So if you do it in the same order with no brackets, it's going to be the wrong answer. So make sure that you factor the inside of the brackets, x plus 4 plus 1. So now we can see that the transformations are a vertical shift. I'm going to use red for that one. A vertical flip first, and then a vertical stretch by 3. And when you're doing it, you should write these in order. The order is just left to right, so we're going to do it in the order A, K, D, and C. I didn't mention that before, so I'll just talk about that right now. So that's the first one, and then this will be the second one, oops, third one, and fourth one. So we'll just write it in that order, just going along. So I'm doing these vertical dilations first, and then I'm going to do the horizontal dilations. Okay, now we've got a horizontal compression by 1/2. Then we're going to go left 4 and up 1. So I'm going to draw that in those colors. And you can see that I'm going to have a maximum of 4 steps. I just do the vertical dilations, horizontal dilations, and then the shifts. Because shifts are kind of easy to do together. So we're going to start with our parent function. The parent function is y equals root x. So I'm going to draw that in there. 0, 0, 1, 1, 4, 2. That's all I've got right now, because I have a pretty small graph. So this is y equals root x. And then I'm going to do the vertical flip and the vertical stretch by 3. So remember that when you do vertical, you're only worrying about the vertical. You're going to leave the x values alone. So this is 1, 1. And I'm going to take this 1 over here, and I'm going to multiply it by negative 3, and that's going to give me my new y value. So 0, 0 stays where it is, and I'm going to get 1 and then 1 times negative 3, which is negative 3. So 1 at negative 3 right here. And this is 4, 2. So again, I'm just going to worry about the y value and just multiply that by negative 3. So I'm going to get 4, negative 6. Connect the dots in a curvy and attractive manner if possible. Okay, that wasn't very curvy or attractive, but okay. Y equals, y equals negative 3 root x. Okay, so that's my vertical flip and my vertical stretch. Then I'm going to do my horizontal compression. So all of these red points, because we always do the next step with our newest graph, all of these y values are going to stay the same, so it's going to be left to right movement, and I'm going to compress the x values. So this one is at 1, negative 3, so I'm going to multiply 1 by 1/2. So this becomes 1/2 negative 3 right here. And this one was originally 4, negative 6, and so I'm going to multiply the 4 by 1/2. So I'm only worried about the x value. So it becomes 2, negative 6. And I will just connect the dots in a curvily and attractive manner and label y equals negative 3 root 2x. So I've used these two now. I've got the negative 3 and the 2, and I'm just accumulating all the different transformations. And then I can take all the green points that I've drawn in here, and I'm going to move them left 4 and up 1, and then I'm going to be done. So I'm going to go take this one, I'm going to go 1, 2, 3, 4, and up 1. This one, 1, 2, 3, 4, and up 1. And this guy right here, 1, 2, 3, 4, and up 1. Connect the dots in a curvy and attractive manner. And label negative 3 root 2x plus 8 plus 1. Or you could have written 2x plus 4 plus 1. And there you have it, transformations. So in this chapter 1 review, we talked about what functions are, what relations are. We talked about domain, we talked about range, we talked about function notation, we talked about the inverse, we talked about transformations. and we talked about the parent functions. I hope you enjoyed it. Thanks for watching, and see you in class.